All right, this is Mr. Gilliam, and today we're going to learn about the law of sines and the law of cosines. I think you're going to like this. Previously, we have been learning about sine, cosine, tangent, and their inverse operations as well as their reciprocal functions. And what we know is that those are all for right triangles. So we need to start incorporating some of the uses of sine, cosine, tangent, and triangles other than right triangles. And so we have this law here. We're going to talk about two laws today, the law of sines and the law of cosines. The law of sines is a relationship that is true in any triangle. Okay, and basically what it says is the relationship between an angle and its opposite is the same for any part of a triangle. Okay, so for instance, if I took the sine of C divided by its opposite side, it should be equal to the sine of A over its opposite side, the sine of B over its opposite side, or the sine of C over its opposite side. They're all equal. They're all proportional. So it's called the law of sines, and it works for the sine function only. So let's take a look at these new triangles here, and what I see right away is that this triangle for sure is not a 90 or right triangle. This one could possibly be, but it doesn't appear to be. And so the ways that we've used to solve for missing side lengths here recently, one of the ways would be like, oh, well, we could just take the sine of 21 and make it equal to the proportion or the fraction, the ratio x over 16. It's not going to work anymore because these are not right triangles. So we have to have a different way of solving for these unknowns. And the law of sines is going to be that explanation to that question. If I know 21 degrees, if I take its sine and we divide it by its opposite side, it is equal to the proportion of 97, or the ratio 97, sine of 97 over 16. All right, and so when I cross multiply, I have 16 times the sine of 21 equals x times the sine of 97. Now remember, this is just a number, so I don't have to round anything, and I can do it all in my calculator for the most accuracy. I'm just going to divide both sides by the sine of 97. That gets my x all by itself, and I'm going to type this whole thing into my calculator all at once. Okay, I'm going to take 16 times the sine of 21, and then I'm going to divide that by the sine of 97. And it looks like I calculated that to be 5.78 about. Okay, so it's about 5.78. It does say round to the nearest tenth, so I should really follow directions. X equals 5.8. All right, 5.8. Now let's think about the ratios here. If a 97-degree angle is 16 is across from the longest side, a 21-degree angle is going to be significantly less than across from the 97-degree angle. So that would make sense. Let's take a look at this next one here as well. This time what I have is an angle and its opposite, and I'm missing an angle and I have its opposite. So again, I can't just use like, oh, just do the tangent of 45 equals 8 over 10. It's not a right triangle. That's not going to apply to this. What I can do is I can say the sine of x compared to its opposite, 10, should equal the sine of 45 over its opposite, 8. And now it's just a matter of solving. So what I'm going to do is I'm going to cross multiply. I'm going to say 8 sine x equals 10 times the sine of 45. Divide the 8 back over. Some people can quickly just say, oh, well, I just can multiply both sides by 10, and then that'll get rid of that fraction, so it would save you a step. But we just keep going this way. Proportion, solving a proportion. Sine of x, we'll do it the long way. Equals, I'm gonna reduce this even. 5 times the sine of 45 all over 4. And so what I have here is the sine of x equal to just a number value. Take 5 times the sine of 45, and I'm going to divide it by 4. Looks like I'm getting 0.8839. And of course, to undo the sine function on x, I'm going to take the inverse sine of both sides of the equation. Okay, and so I'm going to inverse sine that number, and what it tells me is x must equal 62.1 degrees. Okay, So this guy right here is 62.1. Now let's think if it makes sense here. Across from a 45-degree angle is 8, so a little bigger than that angle is 10. That would make sense. Okay, so we're going to say 62.1 degrees. It's called the law of sines, and we can use it on triangles that are not just right triangles. That's why it's so useful. Let's take a look at the law of cosine now, and this is the one that takes a little bit more work to remember. There are some triangles that, of course, the law of sines will not apply to because you don't have the right information for the law of sines. And so for that, a lot of times, what will work is the law of cosines. And the law of cosines says, it's very similar to the Pythagorean theorem. A's, B's, and C's, and all of them, A's, B's, and C's. And but then there's modification. You subtract 2bc cosine A, subtract 2ac cosine B, and 2ab cosine C. So I want you to just look at the similarities here. When I'm comparing A, when I make this equation for A, I have b squared and c squared. Then I'm subtracting twice the b and c and the cosine of A. So the law of cosine starts with the A's and ends with the A's. All right. That's the way I remember it. It's like an A sandwich. Same way for B. It starts with B, ends with B. Everything in between is A's and C's only. Starts with a C, ends with a C. Everything in between is just A's and B's only. Okay? And the relationship goes like this. This length squared, and now remember, this isn't a right triangle, it's just any triangle, should be equal to this side squared plus this side squared. Now that would be true if it was perfectly a right triangle. We could just stop there. However, for any other triangle, we subtract twice this length times this length and multiply that by the cosine of this guy. Well, let's take a look at a couple examples here where we have to use the law of cosines because the law of sines is not going to have enough information. If I attempted to use the law of sines on this problem, I would say, oh, okay, well, the sine of 28 compared to its opposite side, x, should equal the sine of b, whatever that is, we don't know, compared to its opposite side. So you can see we have an equation here with too many unknown variables. So the law of sines is out of the question on this one. I always like to try to do the law of sines before I try to do the law of cosines because I just think the law of sines is a little easier to do. So what I'm going to do is this. I'm going to use the law of cosines because I know that if I'm looking for this side length, x squared, it should be equal to the sum of the other two side lengths squared, 9 squared plus 11 squared, minus 2 times those side lengths times the cosine of the angle opposite of our unknown, 28. Okay, and like I said, it just takes a while to plug in the numbers until you remember which numbers go where. I always start and end with the opposite pair. That's how I remember it. Okay. So x squared equals 81 plus 121 minus 198 times the cosine of 28. And I'm going to continue to simplify. X squared equals 202 minus 198 times the cosine of 28, 174.82, and then I subtract finally. X squared equals 27.18, and finally square root. And again, we don't need the plus and the negative version of the square root because we are doing a distance. We're talking about a distance, so that is not necessary. At the end of the day, x equals 5.2. It does say round to the nearest 10, so 5.2. Let's just check to see if this will make sense here. Across from this obtuse angle is 11, and so across from an acute angle would be 5. That would make sense. So about 5.2. I guess we'll just call it units since there's no unit of measurement on the example. Okay, so this is your first example of the law of cosines. All right, so I'm going to give you a second to write that down. I'm going to erase that so I have room to work out this next problem here. Like I said, again, you always want to try to check to see if the law of sines will work first because I think it's just a quicker, easier process, less chance for mistakes, less chance for errors. So if the opportunity is there to use the law of sines, use the law of sines. Again, if I try to use the law of sines in this scenario, I would have the sine of x over 8 equals the sine of an unknown over its opposite side. Again, the sine of, or the law of sines is not going to be appropriate for this problem. So what I'm going to do is this. I'm going to say, if I'm looking for this degree, what goes with that degree is the side opposite. Even though we're talking about a cosine, we're still looking at the side opposite. Okay, so I know that 8 squared should equal 3 squared plus 6 squared minus 2 times 3 times 6. So yeah, once I use my 8 here, I know that everything else is going to be a 3 and 6 until I get to the very end. I'm looking opposite the 8, which is my unknown, my cosine of x. So now it's just a matter of simplification. And so it's got 64 equals 45 minus 36 times cosine of x. And looks like we're going to get a negative value here. And so the cosine of x equals negative 19/36. We're going to take the inverse cosine of each side. And looks like I get x equals 121.9 degrees, which would make sense. It's a nice looking obtuse angle. So don't get alarmed if you have a negative value over here. You'll learn more about the unit circle and why that's still going to give me a positive angle measure later on in Algebra 2, probably pre-calculus. It works out just fine. It would make sense that across from the biggest angle is the biggest side. So I think we did it correctly. Again, this is the law of cosines, and I recommend you do it after you've tried to attempt to do the law of sines, because as you can see, the law of cosines gets kind of long and sloppy. Even though it's just a matter of simplification, there's lots of places to miss the right button or make a mistake. Let's use one more example here. And this is just a word problem. It's already set up on the side here, but let's read through it. It says, Drew and Hunter are playing basketball. Drew passes the ball to Hunter when he is 26 feet away from the goal and 24 feet from Hunter. So Drew passes it to Hunter. He's 24 feet away and he's 26 feet away from the goal. How far is Hunter from the goal if the angle from the goal to Drew and then to Hunter is 34 degrees? Okay, so we need to know how far Hunter is from the goal. So what I'm going to do is this. When I check for the law of sines here, I see that I could do 34 over x compared to, well, we don't know another angle that we can use in a comparison. We're going to have too many unknowns to use the law of sines. So again, we're going to have to use the law of cosines. The unknown is across from 34 degrees, this x value. I'm going to say x squared must equal, and it's just almost exactly like the Pythagorean theorem. 26 squared is the other leg, and 24 squared is another leg. Okay, or hypotenuse, we don't know, it doesn't really matter. So you have the 3 legs that come first, almost like the Pythagorean theorem, very similar to that. I don't see anything having to do with this again till the very end when I do the cosine. So that helps me remember the formula. Minus 2 times 26 times 24 times, and we're running out of room, the cosine of, and now we go back to the x, this angle, across from it, 34. Well, I'm going to say x squared equals 676 plus 576 minus 1248 cosine of 34. And we just keep simplifying, and this is just the process that takes a while. 1252 minus 1034 0.64, and x squared equals 217.36. And please don't forget that we do have an x squared here. This is obviously not 217. So let's square root it, and we only need the positive value. X in this case will equal 14.74, and it says how far is Hunter from the goal to Drew? Okay,